when we do calculations, we do them on determinants. When we do derivations, we do them on traces. And the relation between determinant and the trace is that determinant is multiplicative and trace is additive. Because trace is related to logarithm of exponent of this thing. So we use all the time that the decomposition using this projection operators or characters is that when we look at evolution operator, it adds to the sum of mutually orthogonal evolution operators. They act on subspaces which cannot mix because symmetry prevents it. If you have invariance and discrete symmetry, then you cannot mix symmetric and antisymmetric functions. Evolution stays within its subspace. And for general groups, it'll do it. For finite groups, there might be 12 representations, and they won't get mixed. And for continuous groups, the simplest case is a Fourier space. So it'll turn out that if you have rotational symmetry, the Fourier components will not mix. So if you're in a subspace of, third Fourier component and its multiples, evolution will stay there. So it'll be easy to understand it for the simplest group, which is SO2 or U1. It'll be just labeled by the Fourier series. And then the theory of continuous group, representation of continuous group is generalization of that. So the simplest example of character is e to the I kx, the thing that you always see when you look at translations and rotations. That's U1 or SO2 character. And what they invented in the 19th century, corresponding quantity for any compact Lie group. And the theory works the same way for discrete and continuous groups. It's quite beautiful. The only difference, continuous groups have infinitely many representations. But you don't care about high representations because the index of representation typically means how many wiggles your function has. So in problems that we're interested in, we don't have a very wiggly things because the dissipation tends to smoothen out the functions, so viscosity or whatever. And same in quantum mechanics. Very wiggly functions are very hard to measure. They correspond to very high levels in the spectrum. So you always get a grip on the bottom of the spectrum. Anyway, I never promised you a rose garden. I just promised to build your character. Thanks.